So I'd like to thank NSF and Blue Waters for the opportunity to present our results here at this nice symposium and for getting us out here. So my name is Andre Schleife. I'm from the University of Illinois in the Material Science Department. And I will talk a little bit about our research on semiconducting oxides and why it's challenging and how we go about that. What you see here is my group as of last summer. So as we're doing a Blue Waters tour, that's why I show you this photo. So we're in the Blue Waters room here. 3 of them are my grad students right now, and then there are a couple of undergrads. Okay, so before I begin, I also would like to acknowledge various collaborators because that work. So we do computational work for these materials, but in pretty much all cases, we need experiment to verify those results, right? And so the first 2 people here, Martin Vandenberg and Klaus Irmscher, are experimentalists who measure optical properties of these materials. The other 2 people, Anderson and Chris, are other computational people who are also working on similar kinds of materials with similar methods. So let me maybe begin by talking a little bit about why these materials matter at all. So I'll talk about this a little bit here on the left part of the slide, and I'll leave this video up. This is a video from Corning. So Corning is a glass company, and they were making this science fiction video basically thinking about what we could do in our daily lives if we have materials that are transparent and conducting. And that's exactly the materials that I'm talking about. So they matter because many of you have these materials in your smartphones, right? If you have a touch screen, you need a material that is transparent and conducting because it has to let the light from the display through to your eye. And if you touch the screen, and then the electricity has to be conducted to the processor and being processed, right? And one of the materials that is being used for this application right now is indium gallium zinc oxide. That works in principle well. The problem is that there's indium in it. And so that is a very rare, potentially very expensive material. And so there's research on the way to replace that, right? So you're trying to find alternatives for materials that can do similar kind of things. So that's, I guess, why I put optoelectronics here. So touch screens are one of these applications. Another thing maybe is related to energy, right? So one of the tokens photocatalysts, or maybe one of the first photocatalysts, titanium dioxide, is also a transparent conducting material, right? And so people are trying to understand optical properties and things like that. So those are exactly the key challenges, right? When you want to kind of describe these applications, what we need to understand, and that is not necessarily well achieved yet, but what we need to understand is optical properties of the materials. For example, optical absorption, that's what I'll talk about today. Excitonic effects play a huge role for that when you do that. I'll show you why and how. And also optical anisotropy can be important to understand for applications, for device applications, let's say. In the future, we haven't done that yet for these materials. We also would like to understand the influence of free electrons. What that means is whenever you put this material in some application, you have to dope it, right? So the intrinsic ideal material is an insulator. And so you have to dope it with free electrons, for example, to make it actually working in a device. And that can impact the optical properties. Okay. So maybe as you can kind of tell from what I said so far, so all these simulations that I will talk about today will be in this realm of this figure, right? So this figure shows you kind of different length scales on which you can carry out computer simulations. On this slide, they use, I guess, some mechanical properties. What you also, this thing doesn't work. What you can also do is even optical properties of a material trace back ultimately to the atomistic length scale, right? So what you see here is both zinc oxide, right? It's the same material, and the only difference between these 2 is the concentration of a certain defect, right? The vacancy in this case, oxygen vacancy. And so as you can see, a macroscopic property like the optical absorption spectrum or reflection and these kind of things ultimately trace back to atomistic properties. And so this talk today will focus exactly on those, right? So what we're trying to understand is how do atomistic properties influence optical properties of a material. And in this case, we do this for 2 transparent conducting oxides. Now, what we do in order to understand it is so-called first principles calculations. And so on this slide, I'll show you a brief kind of outline of how one would go about that. And the very first step is we have to know the positions of the atoms in the material, right? And so again, this is not the main focus of the talk, but it's our starting point in the calculations anyways. And so what we do is we do density functional theory. That is an approach that gives you a good approximation for positions of atoms, say, for example, in equilibrium at 0 Kelvin or something like that. And so we use that approach to get a good guess for what the atomic geometry is, right? So we know where the atoms are. What we then do is, and you'll see yellow isosurfaces popping up here. What we then do is we actually want to describe the behavior of the electrons, assuming that the atoms are in these fixed positions, right? And so we can do, again, either density functional theory or more complicated approaches that I'll show you in a minute to understand allowed and forbidden energy states of the electrons, right? So one can visualize that as an electron densities. These are the yellow isosurfaces. Or you can alternatively plot it as a so-called electronic band structure, where you plot all energy states the electron can have in the Brion zone. So this is what these plots look like, right? So the black lines are these allowed states. The area here, or the part of this plot where there's no state, that's the so-called band gap. And that determines your optical properties because, and this is now the last part of this figure, in an optical absorption process, what happens is a photon comes in, right, enters the material, and then it excites an electron that's sitting in one of these valence states into a conduction band state, right? So the photon will be gone after it's absorbed, and the electron has this additional energy. And so what we need to know is we need to know where are those states in this plot, because that determines from where to where can the electrons go. If we have this figure and we know all these different possible transitions because of optical absorption, and their probabilities, then we can plot something like an optical absorption spectrum that would look like this. And then we know what the optical absorption of the material is. We will not quite use this approach, but we'll use this is a fine picture to have in mind when you think about these kind of calculations. And so what I'll talk about in this presentation is basically this part here. We assume that we did that in the past. And so we want to focus on these two things, because this is exactly these excited electronic states that we want to describe, right? We want to know where the energy bands are. We want to know what the optical absorption spectrum is, because those are exactly quantities that determine optical properties of a material. Okay. What I also want to say is, why is this complicated? And so I have a couple of points here. The first thing is those computational techniques, and again, I'll show you what we use. Those computational techniques are numerically challenging, right? So they lead to large matrices. They run for a very long time. So that makes it complicated in the first place. The other thing, and that's actually part of the research goals in some sense, we don't do exact quantum mechanics, right? You have to use approximations, because otherwise solving the Schrödinger equation exactly would be exponentially hard. So you couldn't do it, and so we have to use approximations. Those typically introduce certain limitations, right? So maybe your approximation works well for one material, but not for the other. This is also part of this research that we're trying to figure out to push the applicability of these approximations. So that's another challenge. The other thing, and I guess here I show you that for indium oxide, which is one of the two materials that I talk about in this presentation. So that's indium oxide. These unit cells can be large, meaning they have a lot of atoms in one unit cell. So we have to simulate all those 40 atoms in the case of indium oxide. Again, for these computational techniques, that's not easy. And that's why we have to use computers like Blue Waters. From an experimental point of view, that can also be difficult, simply because, and this is starting to change now, but for those materials that I'm talking about now, there weren't really high-quality single crystals available. So you couldn't simply say, well, I'm just going to measure that on a single crystal. We don't have to do any calculation, right? So that only starts to come up now when people are actually recognizing that you want to use these materials for applications, that they develop the techniques to even make high-quality single crystals so you can really understand these properties in experiment. Okay. Now, so what I'll do is I'll talk briefly about this part, right? How do we get this band structure? And then I'll spend most of the time actually on the optical absorption, because that's the main point of this work. Great. And so I'll actually unfold the entire slide right away, because I think, well, there's some time. Okay. So now in order to understand how to model, how to compute a band structure, we have to kind of see what is the experiment that one carries out when you measure that quantity. And in the case of a band structure, that would be photoemission spectroscopy. And so in this experiment, what you have is a sample, right? Your sample of your material, and a high energy photon. So this is, in this case, is maybe X-rays. Comes in and excites an electron so that the electron actually leaves the material. And so what remains behind is a positively charged hole. And this process is what we want to model. The problem is that density functional theory, that approach that I talked about in the very beginning, does not do a good job in doing these kind of, in calculating these quantities. And so we have to go beyond. And so now one example of that is shown down here. Unfortunately, you can't really see these blue lines very well. So if we did density functional theory for gallium oxide, what you get for the band structure is these blue lines here, right, and all the other ones in this plot. If you compare that to experiment, you'll see that this band gap is way too small, right? So in this particular case, we obtained, I guess, 2.5 electron volt. The experimental one is closer to 4.9. That is a tremendous difference, because if you think of optical absorption, this is exactly the spectral range that you want to describe accurately, right? And in this case, we use the hybrid functional to reproduce, or not to reproduce, to compute a band structure that is closer to experiment. Again, that was work that we did in the past, but we will use it as input to get optical properties. The take-home message is kind of that this hybrid functional gives us a good band gap in comparison to experiment, so that's good. And then we approximate that by so-called PBE plus delta method, where we use this computationally cheap approach and correct for the deficiency by opening up the band gap to the value that we got with the more complicated approach. And as you can also see, the mismatch at higher energies will not be just a constant shift. So you can see that those bands start to deviate. These are things that we have to tackle in the future. Now, okay, so let's assume we have a good band structure. What we now want is optical absorption. The experimental situation is slightly different in that case. So you experiment, again, we have these bands, right? Occupied valence bands, empty conduction bands, and a photon comes in. Now this photon is not an X-ray photon. We now talk about visible light, for example, right? So in other words, the energy of this photon is much lower, and so the electron will still be in an excited state, but it will not leave the material. The consequence of that is that this electron in the conduction band state and the photon, the hole in the valence band state, they feel each other because they're oppositely charged. So right, you can see this electron is negative, the hole is positive. This interaction has to be taken into account. None of the approaches that I mentioned so far does actually a good job doing that. And so we have to use a different approach, and in our case that's called the Bethe-Salpeter equation. So without going into many details, the Bethe-Salpeter equation is an integral equation. The kernel is this screened electron-hole interaction, so it's not just a bare Coulomb potential, but because we're talking about a real material, there is a certain screening just because this all happens in a real material, right? So this electron-hole interaction is screened. That is something we have to also calculate, this screening. Now let's assume we do that, we get this polarization function, then we can calculate a quantity like the dielectric function. This is something that people measure for these materials. I'll show you that on the next slide. Because this next slide actually is meant to show you why we need to do this approach, right? Why do we have to solve this Bethe-Salpeter equation? And that also leads to why do we use blue waters. Okay, so what you can see here is this dielectric function that I just talked about in the previous slide on the y-axis, and the x-axis is the photon energy, right? The energy of the incoming light. So we have two curves here. The black one is experiment for magnesium oxide that will look like this curve. Now, if we did this HSE calculations I mentioned earlier, we would get something like the red curve, right? Maybe the band gap is kind of right, but because the onset here is at roughly the same energy between the two curves, but then at any other photon energy, there's practically no agreement, right? And so you could not really predict an optical spectrum. Now, if we take into account this electron-hole attraction that I mentioned, then we get the blue curve, right? So you can see it looks vastly different. We get especially two features that are kind of typical. One is this bound state here, right at the band gap. This is so-called bound electron-hole pair. And then we get for higher energy peaks this kind of redshift. That is something that people observe for many semiconductors. What it means in practice is we calculate a large matrix, so-called excitonic Hamiltonian. The matrix of the rank of this matrix can be on the order of 50,000 for magnesium oxide. For indium oxide, we're going to be much larger. I'll show you that in a minute. So we have a large matrix that we now have to deal with. And there are two ways that you can deal with it. You can either diagonalize it directly. That may be doable for a matrix with a rank of 50,000, but it's already getting painful. But if the rank is something like 300,000, then it's more or less impossible. So that makes it computationally expensive. And we use actually a so-called time propagation approach to circumvent that. And if you compare that to experiment, I guess that's what the last slide for this one shows you is we get very good agreement, right? We can describe the positions of peaks very well, sometimes even relative peak heights. So that makes us confident that we actually have predictive power, and we're going to apply that now to indium oxide and gallium oxide. Okay, so let me show you. How much time do I still have? 5 minutes. Okay, good. So let me show you some results. So the first curve that I want to show you is actually kind of zoomed in version of the spectrum close to the absorption band gap, right? The band gap of the material. So the dashed curve is without excitons. That is what I showed you before for magnesium oxide. And the influence of excitons is now large, right? We get a large deviation. That is something you can definitely see in experiment. So we see this pronounced enhancement of the absorption onset. The other thing you see is the onset position shifts a little bit. This is related to so-called exciton binding energy. That is something we have actually not fully converged in this calculation. So the binding energy makes it even more complicated to converge. And then this material is cubic, so there will be no anisotropy. The open question in this case is, how can we really describe this dielectric screening? So in this case, we simply used a model dielectric function, but that is something that we expect to not be adequate necessarily for all energies and all frequencies. So we are looking into that in the future. Now, if you look at the same spectrum across a larger photon energy range, maybe from 0 to 15 eV, our experimental collaborators measured it from 0 to 40 eV, right? So that is really when it gets expensive, because in order to simulate a spectrum across such a large photon energy range, this matrix will be much larger. I guess in this case for indium oxide, the rank of the matrix was on the order of 360,000. That is a matrix of about 1 terabyte. Now, that is hard to tackle, basically, and that is exactly why we use blue waters. One example for a calculation of this one, when we read this matrix, it takes about, if I remember correctly, on the order of 8 hours to just read this matrix into memory. Actually, with Bergerup, we're now trying to speed this up because that becomes a limiting factor. And before we used blue waters, that was not the case, right? The reading step was much faster simply because the matrices were much smaller. But now that we actually can get to these large photon energy ranges, we start running into these kind of problems. So we have to deal with those now. Nevertheless, blue waters allows us to even do these calculations. So that is something that we could not do on a different machine. And so now with this tool at hand, and I think while we're talking about this, I started calculating spectra up to 40 eV because that's what we can compare to these measurements. This will tell us exactly how does the approximation of the screening and how does these quasi-particle corrections influence the accuracy of our results. And then maybe one last example where these excitonic effects are even more dramatic. That's actually gallium oxide. So you can see, again, the dashed lines are DFT and the solid lines are Bethe-Salpeter calculations, and you can see in all cases, right at the absorption onset, you get this huge enhancement of optical absorption. You get this redshift. So in other words, you need to do this approach to describe an optical spectrum if you want to compare to experiment. Otherwise, you're lost, right? Okay, so at this point, to maybe allow some time for questions, I'd like to conclude. So what I wanted to show you is that we do have the computational tools at hand now to calculate accurate optical absorption spectra. However, they are computationally expensive, and so that's why we need machines like blue waters. If we do that, we can get accurate results over a large photon energy range. And in the future, what we want is we want to get rid of or improve on certain approximations in the code, such as the screening in particular. And maybe we can also take this capability to cover multiple length scales. So that will use different codes, but these are the kind of things that we're looking into. Thank you very much. Right. Exactly. So in the 40 eV run is actually something where we found that the fact that these collaborators have the capability of measuring that accurately is actually an opportunity for us to verify exactly these kind of approximations. If you literally just care about a material for optical absorption, you're probably fine if you calculate it between 0 and 5 eV or something like that. But for us, we kind of use this as an opportunity to get good testing material, basically, right? So we can really compare to a good experiment. We can disentangle what's the effect from the quasi-particle corrections, what's the effect of the screening, and so we can kind of improve that. Yeah.
I'm taking notes, but putting on my other hat as a support person, be sure when you get cranked up for doing these really big files like the 1 terabyte.
Yeah.
Be sure to talk to the C's group about exactly like the systematics of how you're structuring the files and how your stride in the files and how many nodes you have reading at the same time.
Right, exactly. And that's, I think that's the kind of conversation but that we just started with Bergerup, because again, this is the first case where we actually ran into this problem, right? In the past, the reading was maybe, I don't know, 1% or something of the total computer time.
Right.
Now this becomes an issue, and we may have to rebuild.
But yeah, I'll give you my card.
That's great.
But we should
Yeah.
talk.
Yeah.
When you get ready to start doing that, we should talk in detail.
Okay.
Because
that would be great.
We'll make your system, your thing run faster.
Right.
And we'll minimize its impact on everybody
Right.
else's file system.
And so the writing of these files actually is not necessarily the limiting factor right now, because it calculates the matrix at the same time, which also takes time. And so I don't think it dumps a ton of data in a short amount of time, but the reading, I think that would be great if we could improve on that. So it reads, right now, each processor reads its part of the matrix one after the other. Yeah.
Yeah.
exactly. No, that needs to be improved. I understand that, but no,
Yeah,
that,
we can fix that.
no, that would be great. Yeah.
Just a quick question. How many racks do you use? How many nodes do you use?
See, that's the thing. The actual nodes is not really the limiting factor here. So we use maybe to write the matrix, we use on the order of between 10 and 60 nodes, depending on the exact problem that we tackle. And for then calculating the optical absorption spectrum, what happens there? It reads the matrix and calculates the spectrum. Again, as long as it fits into the memory, we're good, right? So that could be 20 nodes, something like that. So it's not that we need hundreds or thousands of nodes for that. It's just to have the memory that fits the matrix and the capability to read the matrix in the right time, right? But before we run into wall time issues, things like that. So it's not that this necessarily scales to 10,000 nodes or something.
Good, thank you.